guys, welcome back to chapter 17. We are going to talk about an application of integrated rate law, and that has to do with half-lives. So a half-life is defined as the amount of time required for the concentration of a reactant to fall to 1/2 of its initial value. So what we see here is kind of a busy graph. Let me talk you through it. So what we see here along the bottom, we've got time. So time starts at 0, goes to 300. So left to right, it increases. Concentration of our reactant here, 0 at the bottom, 1 molar at the top. So as we come down, decreasing. So what we see here is they've defined a half-life as 100 seconds. So what we see is when we go through one half-life, so 100 seconds have ticked by, the concentration of our reactant is cut in half. So it goes from 1 molar to 0.5 molar. So the time required for the concentration of the reactant to fall to 1/2 of its value. Now we have 0.5 molar of our reactant. When another half-life goes by, so another 100 seconds, we have the amount that we had will be cut in half again. So we go from 0.5 to 0.25, and then 0.25 to 0.125, okay? So it's not that two halves make a whole, like 2 half-lives go by, everything's gone. We have one half-life goes by, it gets cut in half. Now what we have gets cut in half again, and what we have gets cut in half again. So it's just kind of like gradual, slow process. We're going to talk about the half-life of a first-order reaction. The reason is because half-life of a first-order reaction does not depend on the concentration of A, so it makes the math a little bit easier, and it's not as difficult. Half-life for second order and zero order do exist, and you may run into some problems on the internet for these, but we're not going to cover them in this class. So the half-life of a second order reaction depends on the initial concentration of A, as does the zero order. So we've got this integrated rate law for a first order reaction. Through a pretty simple, straightforward derivation, I can get from this formula to the formula of a first-order half-life. I'm not going to ask you to derive this. I'm not going to ask questions about the derivation, but I want you to see how simple this is to just rearrange this equation. So the first thing I'm going to do is I'm going to move this KT over to the left-hand side of the equation. So if it's negative KT, I'm going to do the inverse. I'm going to add KT. Whatever I do to the right side, I also have to do to the left side. So we've got natural log concentration of A plus KT equals natural log concentration of A at time 0. Now I'm going to move this natural log over to the other side, so I'm going to get my natural logs on the same side, so I'm going to subtract by natural log of A at time t. Whatever I do to this side, I also have to do to this side, so I'm going to subtract by the natural log of A at time t. One of the magical properties of natural log is if I subtract two values, it's the same thing as saying the following. So natural log of A at time 0 minus natural log of A at time t is also natural log of A at time 0 divided by natural log of A at times t. So these two statements mean the same thing. Why do they mean the same thing? I don't know. Ask your math instructor. I just know that that's the case. So that's a truth, that's a fact that we're going to use. So now if I clean this up a little bit, on the left-hand side, I've got just KT. And now on the right-hand side, I've got natural log of A, time equals 0, A, T. So now what we're going to do is we're going to look at, we're going to look at some numbers here, okay, to the right-hand side. So if we're talking about the half-life, I know that when one of the half-life goes by, my concentration of A is going to be cut in half. So if hypothetically my concentration of A at time 0 was 2 molar, after one half-life goes by, the concentration of A will be 1 molar. Okay, I could do 4 and 2, I could do 6 and 3, but I just chose 2 and 1. So if I plug those values into this equation, so concentration of A at time equals 0 is 2, concentration of A at time equals T is half of that, or 1. Now we can plug this into our calculator. So natural log of 2 divided by 1 is 0.693. One more just algebraic rearrangement. So I'm going to divide by K. Cancel. And now I have an equation. So the time of a half-life, that's what that subscript means. So the time of a half-life for a first order reaction will always be 0.693 divided by K. So given that I know K, I could determine what the half-life is for that particular reactant. Or if I know what the half-life is for that particular reactant, I could solve for K. So fairly straightforward equation. This equation is what you're going to need to know how to use. I don't care if you can derive it like I just did, but this is the equation that we're going to need to use. So let's take a look at an example. How might this be asked on a test? So N2 decays from 0.085 to 0.023 in 113 seconds. If this is a first order reaction, what is the rate constant K? And then what is the half-life? So we've got a lot of information that this question is asking for. It's asking us to solve for K. It's asking us to solve for half-life. So how do we get to that answer? So the first thing I'm going to do is I'm going to determine, well, how can I solve for K? I have these two equations for a first order reaction. I'm going to try my simple one first, because why not? So it's asking for the rate constant K, which means I must know the half-life if I'm going to solve for K. Do I know the half-life for this reaction? I don't. That's literally what it's asking for in the second half. So I cannot use this equation to solve for K. I must use that later. I'm going to have to use this equation to solve for K. So let's take inventory of what we know, see what we're trying to solve for. So concentration of A at time T, K, T, and then concentration at time 0. So I know N2 decays from 0.05 to 0.03. So I actually do know both of the concentrations in this case. So this is going to be our initial concentration. The higher number is always initial, because reactants go down. And then our final, or at time T, is the lower number, 0.023. And then the last bit of information I'm given is this 113 seconds. So that's the amount of time that ticked by when our concentration changed. So I know 3 of the 4. I'm going to solve for K. Right now we're going to plug and chug. So plug it into our equation and chug our way through it. So natural log of concentration at time T is 0.023. Equals negative K times 113 plus natural log of 0.085. Now I'm going to plug this into my calculator and start clearing it up. So natural log of 0.023 equals negative 3.77. That equals negative k times 113 plus natural log of 0.085. That gives me negative 2.46. I want to get this k by itself, so I got plus negative 2.46. I'm going to do the inverse and add 2.46. That cancels. Whatever I do to the right side, I also have to do to the left side. We have negative k times 113 equals negative 3.77 plus 2.46. And I get negative 1.31. Now to get k by itself, I'm going to divide by negative 113. So that cancels, that cancels. Whatever I do to the left side, I also have to do to the right side. So negatives cancel, and k equals 1.31 divided by 113. And it's 0.0116. The 1.31 is a unitless number. This 113 has the unit of seconds on it. So the unit for k is 1 over seconds. So that's the first step of the problem. We used the integrated rate law to solve for k. Now the second half of the problem asks us, what is the half-life of this substance? So now that we've solved for our k value, we can determine what the half-life is using our other equation. So now we're going to use the 0.693 over k equals the half-life. So 0.693 divided by our k value, which is 0.0116, 1 over seconds. So the half-life of this particular reactant is 0.693 divided by 0.0116, and we get that it is 59.7. How do we know the units on this? Well, the units are built into the problem. So we've got 1 over seconds on the bottom of a fraction. That actually brings this to the top of the fraction. So you kind of take the inverse of the inverse. And we get that the half-life is 59.7 seconds. So that is an integrated rate law problem with the half-life reaction for a first-order reactant. I hope you guys found this helpful.